Hello, this is Jack Jackson. In this video, we're going to be looking at finding areas, but using double integrals to do that. You say, wait a minute, I thought integrals were for volumes. Well, remember the double integral of a function f of xy over some domain in the xy is assigned net volume between the graph of the function, which is some surface, and the xy plane. But if the function is f of xy equals 1, in other words, the plane z equals 1, uniform height of just 1, the volume is numerically equivalent to the area of that base of the region. Because what we're doing is we're finding the area of a cylinder of constant height 1, and which is just area of the base times the height. Well, the area of the height's 1, so the area of the base and the volume are numerically equivalent. So this allows us to use a double integral to compute a volume. And so we get this formula that the area of some region, which is a domain of the function, is the same as double integrating over that domain dA. So if you do the integral of dA, you get A. Makes sense. Now, when we're doing an integral as a double integral, we've always done these, well, except for when we were just approximating and defining them, we've done them as iterated integrals. And so you want to rewrite that. Well, one thing we've seen is that the dA is just dx times dy or dy times dx. And of course, that comes from the fact that when we're splitting up our region, we're looking at little rectangular subregions of width delta x and height delta y. So the area delta A is just delta x times delta y. So when we take the limits, we get the same relationship among those differentials. dA equals dx times dy. So if it's a type 1 region, we'll integrate with respect to y first, and we integrate from y1 to y2 dy, and then we integrate that with respect to x. But y1 and y2 are usually functions of x. Not necessarily constant functions. They could be, but not necessarily. But then the x1 and the x2 are constants. And this will give us an area, because notice that the function that we're integrating there is just a function 1. So let's do that for an example like that. So if f of x equals sine of pi x, and g of x equals x minus 1 squared minus 1, let's find the area bounded by those two curves. Well, the first thing to do is to graph it. So there's a graph of it. The green curve on the top is the sine wave, and the parabola on the bottom is the bottom of it. And so the graph that's in between there is there. Now the parabola is just going up forever, so it's never going to come back down and touch the sine wave, which is going up and down forever. So this is the only region that's bounded with a finite area. At least by these two curves. Okay, so we want to find this area here. And if we set this up as a double integral, how would we do that? Well, this is how it works. We're integrating the function 1 dy dx. This is more easily thought of as a type 1 region. So if you think of this as vertical strips, the top of the strip is always bounded by this curve, sine of pi over 2 times x. And the bottom is always bounded by this curve, y equals x minus 1 squared and n minus 1. So those are our limits on our inner integral, and we just integrate the function 1 with respect to y. And then we integrate with respect to x. We need to know these points of intersection, but this one has some pretty nice ones that kind of pop out at us pretty quickly. They cross at 0, 0, and at 2, 0. And you can plug those in to be sure that those are exact values. For example, if we plug in 2, in here, pi over 2 times 2 is pi, sine of pi is 0, 2 minus 1 is 1, squared is 1, minus 1 is 0. And if you plug in 0, 0 minus 1 is negative 1, squared is 1, minus 1 is 0, 0 times pi over 2 is 0, and sine of that is 0. So they do in fact cross exactly at those 2 points. All right, so let's do this. We integrate this first function, it's just y, from the top curve, evaluated from the top boundary to the bottom boundary. And if you think back at the way we did this in Cal 1, we just started with this integral right here, which is totally equivalent. We said we run a strip from the top to the bottom, top curve minus bottom curve, and we integrate that with respect to x running from 0 to 2. So this gets us right back to where we were in Cal 1. So you can do this either way, set it up directly here, or you can set it up as a double integral. So continuing on, let's say we square this and distribute. So this is x squared, that makes it minus. You've got minus 2x, and that makes it plus 2x. And then this is plus 1, minus 1 is 0, and so that goes away. Now we integrate this. If we want to do an antiderivative here, we need to let u be pi over 2x, then du is pi over 2 dx. We balance that by putting a 2 over pi out front. And the antiderivative then is just minus cosine of u. Or check it by doing a derivative of this. Derivative of cosine of u is minus, which changes that to a positive, sine of this, then times the pi over 2, and that 2 over pi cancels that, so you're right back where we started. These are just polynomials, so they're pretty easy. Add 1 to the power, divide by the new power, here, and that gets you your antiderivative. Evaluate from 0 to 2. Of course, we're using the fundamental theorem of calculus there. Take this function here, plug in a 2 everywhere there's an x. That's here, here, and here. There, there, there. Minus, same function, everywhere there's an x, here, here, and here. Put 0. All right, pi over 2 times 2 is pi. Cosine of pi is negative 1 times negative 2 over pi is 2 over pi. 2 cubed is 8 times negative 1/3 is negative 8/3. 2 squared is 4. All right, 0 times pi over 2 is 0. Cosine of 0 is 1 times minus pi over 2 is minus 2 over pi is minus 2 over pi, but that minus makes it plus 2 over pi. And the last two parts are 0. When we plug in 0 here and here, those polynomial evaluates out to 0. All right, so the zeros are gone. And 2 over pi plus 2 over pi is 4 over pi. And 4 is 12/3 minus 8/3 is 4/3. So probably the best way to write it is 4 over pi plus 4/3. If you'd rather get a common denominator of 3 pi, then let's see, we're multiplying that by 3, which would be 12. And this one by pi would be 4 pi. So you got 12 plus 4 pi, or 4 pi plus 12 over 3 pi, and we could factor out a 4 in the top. So we might write it that way instead. Either one of these is perfectly fine. There's an exact answer, and we can get a decimal approximation with the calculator. Here's the whole thing worked out with a TI Nspire. They put it in the form, this form here that we first looked at, and there's a decimal approximation as well. Okay, so there's an example there, but what about if we do polar coordinates? So remember that dA is dx times dy, or dy times dx in rectangular coordinates, because each subregion is a rectangle. So delta A is just delta x times delta y. Well, what would be dA in polar coordinates? Well, we're slicing it up into little pieces that look like this little shaded piece here. They're basically a wedge or circular sector minus another circular sector area, and see what's left. Well, this is delta r here. This angle is delta theta. And remember, the arc length is just r times that angle, so it's r times delta theta. Now, what's r? Well, r could be a distance from here out to this point, and that would be this length. If r is a distance out all the way to this side, that would give you this side. Now, they're not the same, but if we average those two and do an r that goes halfway in the middle and do an arc length across there, it turns out that you take that arc length times the delta r, you get this one here. So this r is the average of these two possible r values in the middle. Okay, of the top and bottom boundaries, kind of like a midway curve across here. So that's what delta A is. It's r, delta theta. Well, it's exactly equal to that if you choose the r the way I described it. And dA then turns out to be r d theta dr, or r dr d theta is the more usual order, although we could set these integrals up in either order depending on the function. So notice dA is just dx times dy, or dy times dx if you're doing rectangular coordinates. But when you replace dA with r's and thetas, you got a dr and a d theta, but you also have this extra r. Okay, so let's look at that in an example. So suppose we want to use a double integral to find the area of the region inside the curve r equals 4 cosine of 3 theta, but outside the curve r equals 2. Of course, r equals 2 is this circle centered at the origin, radius 2. R equals 4 cosine of 3 theta is this 3-leaf rows going out or starting out at 3 here, 4, and the 3 makes it 3 leaves. So starting out at 4 here on the x-axis, 4, 0, and it comes back here, and we want to see where that crosses right there. So we're actually finding the area. It's this area here, and this one here, and this one up here, all together, added together. But if you look, that's just 3 times that one of these areas, and within one of those areas, we could kind of split it in half. So if we could just find this area from 0 up to whatever angle this is, where they cross, then that would be this little area. We multiply that by 1, 2, 3, 4, 5, 6. So we just need to find that. Well, one of the first things we want to do is find that point right there. We need to find the theta for that. So that's where we're going to cross. That theta is clearly between 0 and pi over 2. So we want a theta between 0 and pi over 2 where cosine of 3 theta, 4 cosine of 3 theta is equal to the 2, where this r and this r are the same. So substitute the 2 in place of the r there. We have this equation. Divide both sides by 4. We get cosine of 3 theta is 1/2. 3 theta has to be pi over 3. Okay. That comes from one of our standard triangles here. And then divide by 3, we get theta equals pi over 9. So that's pi over 9. And in fact, I graphed this with my graphing utility and told it to only go from 0 to pi over 9, and then I got the red version of the curve, which only traced out of here from 4, 0 back to this point here, where theta is pi over 9. Okay, and so we would find that area right there and then multiply by 6. Okay, so now we want to use a double integral to figure it up. The area that we're looking for is 6 times the double integral dA, where this d is not the full domain, but just this little piece. So this would be dA is replaced by r dr d theta, and the inner integral is the limits on the r's. So if you're drawing a radial line segment out from the origin like this, coming out, it's the part that's going to shade in the area, it always has an inner boundary of this r, which is 2, and an outer boundary given by this curve out here, which is 4 cosine of 3 theta. And the thetas then are going to run from 0 to pi over 9. So there we go. So notice what happens when you integrate r, you get 1/2 r squared, and we're going to evaluate it from the bottom, the inside curve to the outside curve. So this is 4 cosine of 3 theta squared minus 2 squared. If you look at it, that's how we set it up a couple videos back, where we integrated this area between two curves, just like this. We did, it's 1/2 r squared, 1/2 big R squared minus little r squared, big R being the r on the outer curve, little r being the r on the inner curve. Okay, in this case, the 1/2 times the 6 is 3. And so here we have our r squared and the other r squared. Okay, so 2 squared is 4. I'm going to go ahead and distribute the 3, so that makes that 12. This is 4 squared is 16 times the 3 is 48. So I'm going to leave it like that for the moment. I'm going to break this into 2 antiderivatives and add them up in a minute. But first, I'm going to have to, one of them is going to involve a cosine square. So I need to reduce that power down to 1 by using the power reducing identity. Cosine square of 3 theta is 1/2, parentheses 1 plus cosine of twice the angle, which would be 6 theta. All right, let's see. 48 times 1/2 is 24, times 1 is 24, minus 12 is plus 12. And let's see, what was it again? 48 times 1/2 is 24, so we have a 24 here. The 24 I want to think of as 6 times 4 and split it up like that. So I have plus 12, the integral of d theta, which is just 12 theta. And here I have the cosine of u du. Du is, u is 6 theta, du is 6 d theta. 6 times 4 is the 24 that we had up above. And so the antiderivative is just sine of u. Okay, when evaluate from 0 to pi over 9. So take this formula. Everywhere we see a theta, there and there, we put pi over 9 minus, same formula, and put in 0 for theta there and there. Okay, that 4 should be inside there. Okay, there we go. All right, not that it's going to matter because this is 0 and this is all 0. So this whole thing is 0 here. 12 divided by 9. See, we can cancel a 3. So it leaves a 3 in the bottom, a 4, and then that pi in the top. Let's see, 6 and a 9. That'll cancel a 3 there. So that gives us 2 pi over 3. The sine of 2 pi over 3 is the square root of 3 over 2. The 2 times the 4 cancels, leaving a 2 there. So it's 2 square root of 3 plus 4 pi over 3. If we wanted to factor out a 2/3, or in other words, essentially get a common denominator, then we'd be left with, I'll switch the order to 2 pi times plus 3 square root of 3 times the 2/3. Either way, you get approximately 7.65289. I'll use this one I've got boxed in as my exact answer. And the calculator gave me something more like my second version. So here's the integral in the calculator, and we see it did get the second version there. If you look at it, if you distribute the 2 here, well, there's the 2/3 out front, and then out top you get 2 pi plus 3 square root of 3. That's the same as this. And there it is in a decimal, which is where I got that. So what we were able to do in this video is see that we could use a double integral to find an area, but that area differential, dA, depends on whether you're in rectangular or polar coordinates, how it turns out. Either it's dx times dy, or dy times dx, or it's r dr d theta, or r d theta dr if you want to switch the order.